Right, hello guys, and welcome to one of our buffer overflow series. And today we're going to be looking at how to bypass or defeat DEP, which is data execution prevention, using return-oriented programming, also known as ROP. And before we get into the nitty-gritty, I just want to talk about what DEP is all about, or what it is actually about. So DEP stands for Data Execution Prevention, and it's a security mechanism on Windows operating system that marks all the memory locations in a process or in a program as non-executable. So unless the memory region initially by the application already contains some sort of instruction, DEP will allow that to run. However, if an attacker or a user tries to insert code into this non-executable memory locations, which DEP has actually turned off, an exception will be raised. So in essence, what we're saying is, the memory location where we have user data input, DEP actually turned that off. Because the problem is, because the reason most buffer overflow occurs is, a CPU treats both data and instructions as the same. So what happens is DEP actually disables the execution of code in this memory region in order to prevent execution of code. And I'm going to explain that in much more detail, and we actually have to see how that works. So at the moment, I've got a Windows 7 machine, and I've got my offensive box, which is a Kali Linux machine. And we've got the application ASLR actually running on this Windows 7. I'm just going to have a look at the application, which is installed on this machine, and I'm going to go to the control panel, and we can see here we've got the ASLR actually started and actually running. I've also got an exploit which I could show you, a working exploit, and this exploit contains a shell code. We've got our buffer, some junks, the jump ESP instruction, and our shell code within this exploit. And what I'm going to do is show that at the moment this exploit actually works. So I'm going to be listening on port 443 and send this exploit. Right, and you can see it succeeded. We do have a shell, and we've been able to compromise the Windows 7 machine using the buffer overflow saved return address exploit. Now, as a compromise, if we do an IP config, we can see the IP address of the Windows 7 machine, which we can also confirm here. Okay, so we can see we do have access into this machine. So what does DEP actually do? So what we can do is we could turn on DEP by going on to computer properties, advanced system settings, and under the advanced tab click on settings, and we do have data execution prevention here. And you can see here it says data execution prevention helps protect against damage from viruses or other security threats. And at the moment, by default, it is turned on essential Windows programs. So this is designed to protect Windows program. But what if you have another, a service or an application, just like the ASLR we've got? DEP is actually by default not actually protecting that application from perceived threats. So by choosing these other options, which says turn on DEP for all programs and services except those I select, will actually make DEP to be activated. So I'm going to click on apply. It says the changes you have to restart the system. So I have to restart the system in order for the process to be completed. So I'm just going to do a quick restart. Okay, so the idea of DEP is to prevent the memory region from being executed. So this is the exploit, the POP3 exploit at the moment, which we've got. We'll just open it up in text editor, and once we apply DEP, once we applied a ROP to defeat DEP, we're going to have an exploit that's similar to this. So I'll close that for a moment and just wait for the Windows 7 machine to reboot. I'm also going to exit the shell, clear screen over here. Right, so we can confirm DEP is actually being turned on. So I'm just going to go in here and have a look. And we can see here DEP is actually turned on. Right, so what we can do is we could see if we could start the ASLR application if it's not already running. And we can see here is actually running, and I'm going to attach the running applications or the running service to Immunity Debugger just to see what happens when we send the exploit again. So just going to make sure it's running, so we can see at the bottom right corner the application is up and running. So let's try to send our exploit once again. So I'm going to just set up a listener on 443 like we did before, and you can see the exploit has been sent. However, we do not have a reverse shell. So we can see here the exploit is actually still running. The application is actually still running. I'm just going to close this, stop the application, and start it again. I'll close the application. I'll open up the the control panel again. I'll start the ASLR application once again. I'll attach it to Immunity Debugger. And run the application. Once again, I'm going to send the exploits. The exploit succeeded. However, we do not have a network connection. Now, we can notice here Immunity Debugger has crashed. We do have our jump instruction, an EIP, and you can see an exception has been flagged. So access violation when executing, this instruction, and Immunity Debugger has paused. So an exception has been raised because DEP has been turned on. So when we're talking about the memory region, DEP has actually turned off, for no execution of instructions. We're actually talking about all of this region. We've got EBX, ESP, EBP, ESI, and EIP. So all of this memory region has been turned off, not to, or has been instructed not to execute any instructions. It could take in data, but any instructions would actually send a flag. So how can we defeat this DEP protection mechanism? So we're going to talk about something called return-oriented programming, and what this is actually doing is we're using existing code, code that already exists in the program we're exploiting, and we're going to then generate what we call rope gadgets in order to turn off DEP, so that this memory region can then execute instructions just like before. So what I'm going to do is I'm going to close. No, I'm not just going to close that. What I'm going to do is I'm going to use the Mona Python module in order to generate our rope gadgets or rope chain. So I'm just going to type in Mona ROP -m, which is like, you know, look for any wildcard modules, DDLL. So I'm saying look for any module, tag N, tag C, PB, and then I'm going to say do not include any of the bad characters, which is, you know, what we identified when we, you know, conducted our exploit initially. 0D, just to make sure. 0A, X, 0, X, 0D. Right, so I'm going to tell Mona to look for a rope chain which we could actually use. So Mona is going to search all through the program for a bunch of code that we can use in order to turn off DEP. So this might take a while. This depends on, you know, how fast your computer processor is in order to generate these rope gadgets which we're going to be using. So once this is completed, a folder in the Immunity Debugger folder, we're going to have a file where we can then copy our rope chain or our rope gadgets in order to include in our initial exploits, and hopefully that will enable us to actually have access once again to the machine remotely, in order to exploit the Windows 7 machine remotely. So what I'm going to do is, because this is taking a bit of time, I'm going to pause the video, and then once it's completed I will then come back to complete the exploit.